Thanks, Tom. Thanks a lot for this invitation. I'm really sorry I couldn't be there in person. Okay, so today I'm talking about, it's mainly work with Amir Dembo, but it's based on an approach to large deviations for random graphs and hypergraphs actually that we developed with Tuan Pham. So I might get to mention a bit of this, but that's sort of stuff under the hood. Okay, so what is an exponential random graph model? So this is a class of measures on finite graphs of a given number of vertices. N is always going to be larger going to infinity. And these, it's a family of generalizations of the Erdős Rényi model. So to fix some notation, I'll write script gn for the set of all simple graphs over the labeled vertices 1 up to n. We'll often think about this as the discrete hypercube. So for every, you can identify a graph with a, say, a 0, 1 symmetric matrix where you have a 1 at pair ij if there's an edge between I and j and 0 otherwise. So that the notation will sort of abusively treat these like points in the hypercube or like matrices. But if it's ever confusing, you can stop and ask me. Okay, so an ERGM is a probability measure of the following form. So we write it in a sort of statistical physics-like way. Actually, I didn't check. Are you able to see what I do with my cursor?
Yes, we are.
I think so. Okay, great. Okay, so it's of the form. So it's a exponential families. We have so it has a probability mass function on this finite set of the form an exponential of, okay, so we scale by n squared, which is sort of the order of the number of edges in the graph. And then we have some Hamiltonian function of the graph that also depends on a vector of parameters. And then we have an additional term. I could have put it in with the Hamiltonian, but it's convenient to keep it separate, which counts the total number of edges in the graph. So here I write Gij for this indicator variable that, so it's a Boolean variable that's 0 if there's an edge between I and j, and 1 if there isn't, so that this counts the total number of edges. And so we have a vector of parameters beta 1 up to beta m, and an additional parameter alpha that's in front of this edge count, and a normalizing constant. Okay, and the Hamiltonians take this form. I mean, so any measure you can sort of write as the exponential of something, but the Hamiltonian has this sort of form for the case of ERGMs. That it's a linear combination of some collection of graph statistics that you're interested in, of sort of giving preference to or trying to suppress. So I'll give some examples, but so we have some fixed collection. The M is bounded independent of n, so some fixed collection of graph statistics. We have this Hamiltonian that's a combination of these, and then we have a sort of parametric family of distributions of this form. Okay, so just as a couple of simple examples, the simplest example is where you just don't, you just take the Hamiltonian to be 0. So you don't give any sort of positive or negative weight to any sort of graph statistics. All you have is this edge count having some weight. Alpha we let just be a number on the line, but you could parameterize that in this way for p between 0 and 1, and then you can see that the probability mass function just works out to be the probability mass function for the Erdős Rényi graph. Okay, so for any fixed graph, it gets this probability that depends only on the number of edges. So this parameter alpha will determine the sort of sparsity of the graphs. So I've put a negative sign here, which means that if alpha is large and positive, then the measure sort of favors graphs that are relatively sparse. Okay. All right, so how about something less trivial? So probably the most studied model is the edge triangle model. And so here's an example of what I could take to be one of these statistics F, which is, in this case, is the density of triangles in the graph, which we can express in this way. Okay, so this is sort of graph theory notation for it's the so-called homomorphism density of the triangle, so the complete graph on 3 vertices in the big graph. So the way you can think of this is, so this is the probability where if you select 3 vertices uniformly and independently at random, it's the probability that those form a triangle in the graph. Okay, so we just have these Boolean indicators that all 3 of those potential edges are there. And we count them all up, and then it's normalized by n cubed, so that it's a density in some sense. So it's the probability that you see a triangle when you sample 3 vertices uniformly and independently. Okay, so and then we just have a single beta. So for the edge triangle model, you just have 2 terms. You have some weight on the triangle density and then another weight alpha on the edge density. Okay. All right, so some background. So these models go back to the 80s. And they were introduced in the social sciences literature, and so the hope with this class of distributions, so they were starting to get interested in sort of network science and social networks, and the hope was that they could do parametric statistics on large networks by sort of introducing these sort of parametric families of distributions. And then, so the hope was that with it, you could sort of do model fitting. You would specify some statistics that you're interested in, sort of favoring or deprecating, and then you could estimate the model parameters through sampling. Okay, so all right, so these were sort of the 2 of the earlier works that advanced these models. So I think this work from the 80s was just looking at edge triangle, the edge triangle model. Okay, so one thing that they really wanted to see with these models, they wanted to have a class of random graphs that they could tweak to exhibit what they call a transitivity property. It's an important property of social networks, which is that friends of friends are more likely to be friends. So this is not something that you get with the Erdős-Rényi graph, but I think it's natural to guess that maybe if you do something like with the edge triangle model of taking a positive beta parameter multiplying the triangle density, if you're sort of tilting the distribution to favor more triangles, then I think it's reasonable to expect that you might start to see some amount of transitivity in the graph. Okay. The separable form of the Hamiltonian, like this, so sort of for the practice of statistics, this is sort of convenient because it means that these statistics are sufficient statistics for the corresponding model parameters. And Okay, and so when they then go to estimate the model parameters, they would tend to use so if you're going to use maximum likelihood estimation, then you need some estimate for the size of the partition function, and for this, so they would typically estimate this using sampling algorithms of various MCMC type algorithms. Okay, so so this was the hope, and they started using this framework, but from early on there were some problems that were noticed. So you know, and this was coming from people in the social sciences community, not you know, so to their credit, they were noticing some of these problems, and I'll just highlight sort of 3 of the main problems that were pointed out. So with this program, so the first problem was that for sort of large ranges of the parameters, even with the edge triangle model, they would actually still not see any transitivity, which is certainly a problem for modeling social networks. Another sort of problem that they observed was what they called degeneracy. So a particularly sort of egregious form of degeneracy is if so they would draw samples from their distributions, you know, for various values of the parameters, and and just look at what the graph looks like, and they would see either a graph that was almost empty, so almost no edges, or a graph that was almost full, almost the complete graph, and they'd get a sharp jump from sort of almost empty to almost full, as say that this beta parameter for the number of triangles passed through some threshold. So more generally, that they use the word degeneracy to mean that the distribution sort of concentrates on a small number of of graphs with trivial structure. So this is the worst form of degeneracy, where it's just concentrating on the empty graph and the full graph. And then they also found that their sampling algorithms were not converging very fast in some regimes of the parameter space. Is there a question?
Niet helemaal, ik wil niet alles geheel zetten. Dat het hele gaat. Het ook al natuurlijk.
Ja, maar dat is niet de bedoeling.
Nee.
Was there a question?
I don't think it was a question.
Okay. Okay. So eventually, some mathematicians and statisticians came along to give some rigorous explanations for what's going on. So I think one of the first major works of this kind was of Bamidi, Bressler, and Sly, who considered this class of ERGMs, where the so the most studied case for these, you know, these functions fk are where where it's the density of some fixed collection of graphs, capital Fk. So the edge triangle model is of this type, where m is 1, and then f you just have f1 is the triangle. But you could do the same sort of thing. You can extend this definition in the natural way to, you know, have the density of any other fixed graph. Okay, so for ERGMs of this type, where the graph statistics are these homomorphism densities for a fixed collection of graphs, they prove the following result. So it's a really nice result, but it's a negative result. So what they showed, so they considered the case that all of these betas are positive, which would you would be taking them positive, for instance, if you want to see some transitivity. And they showed that the parameter space, so the alpha with alpha and all the betas, it separates into two sets, two domains. There's a so-called low temperature phase and a high temperature phase. So if the parameters are taken from the low temperature region, then MCMC algorithms are going to take an exponential in n time to converge. So you just won't see them converge in your lifetime for reasonably large graphs. On the other hand, in the high temperature, what they call the high temperature phase, you get a pretty reasonable convergence time, but the typical samples look like Erdős graphs. And in particular, they have no transitivity. So either the sampling is too hard or sampling is easy, but the graphs are trivial. Sorry, it's not scrolling. There we go. Okay. All right, so the next important rigorous result that I want to highlight was of Chatterjee and Diaconis in 2012. So they used this large deviation principle that was proved with Varadhan. So that Chatterjee and Varadhan established a large deviation principle for the Erdős graph in this so-called cut metric. And they were, so when you can do large deviations theory, then you can, do things like estimate partition functions and study Gibbs measures like these. And so they did this, and so using the large deviation theory, they were able to establish, give an alternative way for approximating the partition function. So in practice, they were doing this through sampling. But there's an alternative way, a variational approximation known as the naive mean field approximation that I'll talk about in a couple of slides, that they were able to rigorously establish for these sorts of models. And they also established a sort of negative result where, so again, for these sorts of models in this parameter regime, they showed that the ERGMs are always sort of mixtures of Erdős graphs. So when I say mixture, I mean that the parameter P is drawn from some distribution, and then with that P, you draw an Erdős graph. So in some sense, the measures are looking like mixtures of Erdős graphs. Okay, so even in the sort of exponential convergence time regime, it's just taking a long time to hop between sort of one density and another density, but they're still sort of trivial looking. Okay, so these are two they're very nice, but very negative results for these sorts of models. But I also want to highlight a positive result that was shown in the same year by Lubetzky and Zhao. So they considered this class where now we're just looking at the density of a single graph F, not some fixed collection, although it was kind of clear that their idea could probably be extended. And they showed, okay, so here we have a fixed graph. So they considered the case that the graph is a regular graph, so delta regular. For the triangle is 2 regular. And they were able to show that for this model, you can sort of fix the at least the degeneracy phenomenon by rather than just taking the triangle density or the F density, you take that function, but you raise it to a fractional power. So they were able to show that if you raise this function to a power, some fixed power between 0 and the max, or the degree divided by the number of edges, then samples will no longer look like Erdős graphs, but they'll actually have some non-trivial structure. They didn't actually say what that structure is. They just proved that it doesn't look like Erdős. Okay, so this gives some hope, and we're going to explore this this phenomenon further. And then shortly after that, there was a surge of work on the so-called quantitative nonlinear large deviations theory, starting with this work of Chatterjee and Dembo, and further developed by Ronan Eldon and others, that allowed for some of these results to be extended to sparse graphs. And so by sparse, I mean not dense, and by dense, I mean with p fixed. So all of these previous results, things were scaled in the exponential so that typical samples will have on the order of n squared edges, which I call dense. So this nonlinear large deviation theory allowed for some of these results to be extended to the case that the density is going to 0 with n. Okay. All right, and so in particular, there was a result of Eldon and Gross using Eldon's approach to nonlinear large deviations, where they were able to show that in a certain range of sparsity, that these sorts of measures are sort of concentrate on sort of stochastic block models, where it's a generalization of Erdős Rényi, where you sort of partition the vertices and then you specify the density between different blocks of vertices. Okay. All right, so for our results, the results I want to describe with Amir are about sparse ERGMs. So of course, most social networks that you'd want to study don't have a constant edge density. So we want to be able to let, say, the parameter p for the edge density go to 0, or this alpha parameter, let it go to infinity. So to do this, we have to do a bit of rescaling from how I set the model up on the first slide. So we study a general class of measures that it's more general than just taking linear combinations. So from a practical standpoint, it was nice to have linear combinations of subgraph densities, because then these were sufficient statistics for the model parameters. But our arguments work just as well if you have any sort of function of a collection of subgraph densities. The only important thing is that it not grow too fast. Okay, so we have some fixed function h on Rm, and so you plug in the subgraph densities, but now that we want the graph to be sparse, the probabilities say that, you know, when you sample vertices at random, that you see a copy of f1 there, it's going to shrink with p, so we have to rescale. So the probability will be about the density raised to the number of edges in that graph. So here we rescale so that these arguments are typically of order 1 for a graph of density p. Okay, so this, you know, I wrote earlier what this means in the case of triangles. So this is sort of a formula. This is just saying in math what I say when I, you know, this is the probability that if you sample, you know, the number of vertices of f, if you sample that many vertices from the big graph independently and uniformly, then this is the probability that you'll see a copy of f on those vertices. So this is just multiplying together the indicators that you have all of the edges you want. Okay, so that's the so-called homomorphism density. Okay, so we also have to rescale, put a different scaling in front of the Hamiltonian. So this has to be scaled by the sort of the large deviation rate for these random variables. And so that turns out to be, so just believe me when I tell you that, so it's no longer n squared, we have to scale it, it's smaller, we have to rescale it by p to the degree of these graphs times log 1 over p. Okay, so with all of that, we can now define our sort of generalized ERGM models as follows. So here I write it as a tilt of the Erdős-Rényi measure. So so the probability that so the measure assigned to some collection calligraphic E of graphs is given by this tilted measure. So this is a tilt of the Erdős-Rényi measure, where I tilt by the, I reweight the distribution by the exponential of R times the Hamiltonian. And so our normalizing constant now is just the exponential of the moment generating function for the Hamiltonian. Okay. So, on the first slide, I could have also phrased that, arranged that like a tilt of the dense Erdős-Rényi model. Okay, so we want to apply large deviations theory for the Erdős-Rényi model, and so it's more convenient to set things up as these up as tilts of the Erdős-Rényi distribution. Okay. Okay, so our first results are concern this this so-called naive mean field approximation. Here I'm just repeating the definition of the measure. So it gives weight proportional to the exponential of our Hamiltonian, and then there's a normalizing constant. Okay, so this naive mean field approximation gives a nice alternative to sampling for approximating the normalizing constant. So to motivate this, first just recall that we have this identity, the Gibbs variational principle, or also known as the Dunsker-Varadon variational principle, which is a variational identity for exponential integrals, or in our case, sums of exponentials. So this moment the log moment generating function is given by the supremum over all measures mu on the set of graphs of the expectation of what's in the exponential under this alternative measure mu, and then you pay the relative entropy between this candidate mu and your reference measure, which for us is the Erdős-Rényi measure. Okay, so the exponential, so the moment generating function for R times this function under the Erdős-Rényi law is given by this you optimize this over all measures mu. Okay, so it's not just going to be optimizing the exponential, so that's sort of the supremum. You sort of have to take the level that also gives has sort of relatively high entropy. Okay, so this is like a two-line of proof or something using Jensen's inequality. This is a pretty elementary identity. All right, and it's not useful. It's not very useful. So this is a variational identity, but it's not useful in practice because you're taking a supremum over all measures over some set of size that's exponential in n, right? So that we have this hypercube of all graphs on vertices 1 up to n, which is of dimension n choose 2, and then the number of the dimension of the set of probability measures over that set is exponential in that. So so this isn't useful in any practical way. But so the naive mean field approximation gives sort of a much more tractable variational problem over a much lower dimensional set. And it's not always true, but when it is, it's nice. So this approximation posits that the supremum is roughly attained on product distributions. So you can just, it suffices to look at product distributions, which is a much lower dimensional set. For product distributions on the set of graphs, you can parameterize these. So these are sort of inhomogeneous Erdős-Rényi graphs, where the So edges are still appearing independently, but each one may have a different probability of appearing. And so we can summarize those by entries of a matrix Q. So Qij is the probability that edge ij appears. So we're looking, so we parameterize the set of these distributions by their sort of weighted adjacency matrices, which is you can identify with the solid cube. Okay, and so then the naive mean field approximation posits that you can just look over the supremum over the product distributions, and then okay, so it turns out you have enough concentration that this expectation under the product under this product distribution is roughly the Hamiltonian evaluated at that weighted adjacency matrix. Okay, so this is what we'll call the naive mean field approximation for the normalizing constant. So I'm going to write that as psi. Okay, and then over here, we've just, since you have a product distribution, the relative entropy just splits into a sum over the relative entropy of Bernoulli's with respect to the reference Bernoulli P measure. Okay. All right, so this is so this is the sort of approximation that Chatterjee and Diaconis established in the dense case. And so we extend their result to allow P going to 0 at some polynomial rate in this general setup where we have some general function H that you plug these subgraph densities into. So for any H that's continuous and non-decreasing in each argument, as the crucial hypothesis is that your Hamiltonian cannot grow too fast at infinity. And it's actually the exact same condition that Lubetzky and Zhao noticed. So it's, you really need that, so if we were sort of just taking these and raising them to a fractional power, for instance, that fractional power needs to be smaller than the degree, or in our case, the max degree, divided by the number of edges. So as long as your Hamiltonian satisfies this growth condition, then the naive mean field approximation holds. So the log moment generating function is to leading order. So it turns out, sort of outside of some trivial boundary cases, that both of these are of order this rate parameter. And so up to subleading order corrections, the naive mean field approximation does hold. So this gives a way to estimate the partition function without using sampling. Okay, so now this applied also, we in this result we can also allow P to be fixed. So this is a sort of also generalizing the Chatterjee-Varadhan, Chatterjee-Diaconis, sorry, result to these sorts of Hamiltonians. But when P is going to 0, we actually get a further dimension reduction. So now rather than optimizing over the cube of dimension n choose 2, we actually get a further reduction to a 2-dimensional optimization problem. So when P is going to 0, then the log moment generating function normalized by this large deviation rate converges to some function psi, which is just optimizing this function. Okay, so up here, it's the rate times the Hamiltonian minus a relative entropy, and here we get this reduction to, so this was this sort of fixed function for the Hamiltonian, and then this is sort of what the relative entropy scales like asymptotically. And okay, so and we have some fixed, for each function f, there's an explicit function tf, so that this result holds. So it's a formula, but it would take half a slide, and it's not worth it to show you what it is. the point really is, so, where are these functions coming from? So just recall that the Hamiltonian was defined where I have this fixed function h, and then I'm plugging in these normalized subgraph densities. And so what this is sort of suggesting, and it's true, is that asymptotically, the measure is concentrating on a family of graphs that can be described with two parameters, and the subgraph densities have this behavior on that family, on that two-parameter family. So asymptotically, after normalization, the subgraph densities behave like a function of two variables. Okay. All right, so, and we can actually describe what that two-parameter family is. So this is our second class of results. So beyond justifying this naive mean field approximation, we're actually able to establish sort of the structure of typical samples from the distribution. So if you sample an ERGM from one of these, under these hypotheses where the Hamiltonian doesn't grow too much and the p is decaying at a certain polynomial rate, then we can actually tell you what the graph is going to look like with high probability. So it's a two-parameter family of graphs that look like this. So here I'm sort of sketching what the graph looks like. Here I'm sketching what the adjacency matrix looks like. So if you're a numerical linear algebraist, you might prefer this picture. But in the graph, it basically looks like an Erdős Rényi graph in most places. So that's the light gray here. But then you have two small sets, I and j, of vertices. So on the set I, it's very dense. It's almost density 1. So you have an almost complete graph on the set I. And then from j, you have this set, the graph is almost complete between j and its complement. So we call j a hub because so in this graph you're able to get from any point from A to B in 2 steps by going through j. Okay, so here this just says in math that the graph is almost complete on I, so you have almost the maximum possible number of edges on the set of vertices I, and you have almost the maximum possible number of edges between j and its complement. Okay, so the set of graphs where these measures concentrate, they concentrate in a set of this form. So we have 2 parameters a and b that specify the sizes of I and j, and then they're in a small neighborhood of this set. So that's what epsilon is. So the almost clique is of size that scales like p to the max degree over 2 times n, and then we parameterize with the parameter we scale it by square root a, and then the almost hub has size b times p to the delta n. Okay, and then we just take the union over all possible positions for these almost clique and almost hubs. Okay, so this is the sort of set of graphs that have an almost clique and an almost hub of these given sizes in terms of a and b. And so our structure result says that okay, so as in the previous result, we're now letting p also tend to 0. For any fixed epsilon with exponentially high probability, if you sample a graph from this ERGM measure, then for large n with exponentially high probability, your graph will lie in one of these sets. And so all I have to do is tell you what a and b are, and the a and b are range over optimizers of this naive mean field free energy psi. Okay, so maybe I guess so psi was this this variational problem. Okay, so you have some collection, some set of optimizers. Often it's just a single point, A comma B, but sometimes there's more than one point that optimize this. And then the graph will look like one of these graphs where A and B are one of the optimizers. Okay. All right. Yeah, so then we also have a different result that sort of expresses how close your sample is to one of these graphs in terms of a spectral norm, but I won't state that one. Okay, so I'll just so I think I just have a few minutes left. So I'll just end with us some pictures that gives the sort of phase diagram for a couple of examples. So so let's go back to the edge triangle model. So what does the edge triangle model typically look like? Well, so following Lubetzky and Zhao, we know that we shouldn't just take the edge triangle model as it's been studied for decades now. We should actually take that function and raise it to some fractional power. And the fractional power has to be at most the max degree over the number of edges, which for this is 2/3. So 1/3 is okay. All right, so we have a Hamiltonian, which just is parameter beta times this normalized triangle density. Okay, so sort of, you know, this we're looking at large deviations, so it'll be at least 1, and then we raise to a fractional power 1/3. So what our result says in this example is that we have the following phase diagram for beta. So as beta increases, when beta is below 16/9, then with very high probability, the graph looks like it just has a single hub and there's no clique. So it's an Erdős graph with a planted hub, and that hub has the parameter B is 1/3 beta to the 3/2. Okay, and then as soon as you cross this this threshold 16/9, then with high probability, it switches to a graph, an Erdős looking graph with a planted clique of size beta squared p to the delta over 2 times n. Okay, so this is a sort of phase diagram. It's a bit cooler looking if you consider models where you have 2 different terms in the Hamiltonian. So this is another model that goes back to the 80s where they looked at densities of triangles, but also densities of paths of length 2. Okay, so we're going to do that, but we also need to raise to a small fractional power, which we take to be 1/3. So now we have 2 parameters, 2 model parameters, beta 1, beta 2, and this is the phase diagram. So this model extends the one from the previous slide, so by going sort of into the beta 2 direction. So if beta 2 is 0, then we just have this edge triangle model from the previous slide. And then, so you can see on the beta 1 axis, we have the same picture as from the previous slide. But then if you additionally have this other term, so as you allow beta 2 to be positive, then you extend into the plane in this way. So you have this boundary here. But when beta 2 is positive, you will always have a hub. So there will always be a hub of a certain size. It's only when you're actually on this segment, this ray of the beta 1 axis, that you don't have a hub. Okay. All right, so I don't have time to sort of describe the large deviation theory. I'll just make a couple of final remarks. So in the proofs, we're using a lot some approaches to nonlinear large deviations that we developed with Tuan Pham, and we're also looking at the analysis of the resulting naive mean field variational problem, and there was a nice so we're building on work of Bhattacharya, Ganguly, Lubetzky, and Zhao on this. The main work that we have to do for these results on ERGMs is to do a stability analysis for this naive mean field problem. So this is where So basically, we have to show that so these guys solved the optimization problem, and it was them who sort of pointed out that these clique or hub structures will, in large deviation setting, these will be sort of these will optimize. And so what we have to show is that those are the only optimizers, but also that those optimizers are stable in the sense that if you're very close to optimizing, then the graph has to look very close to one of those optimizers. And so this actually took a lot of work. Okay, we could extend all of this to hypergraphs, and there's been a little bit of work in the social sciences on this, so that could be an interesting direction. Okay, there's been related work on the structure of graphs, so not in this sort of grand canonical ensemble sort of setup that we have, but in the sort of canonical ensemble where you actually pick a graph uniformly under a hard constraint on counts of edges in a graph. Okay, in terms, what we've done with this fractional power following Lubetzky and Zhao is we've cured this form of degeneracy where you just see an almost empty graph or an almost full graph. But we've still shown that the measures concentrate on this 2-parameter family. And I think this 2-parameter family still is not rich enough to model social networks. I mean, hubs are sort of one kind of sort of phenomenon that you get in some social networks. And cliques are another, but social networks tend to be much more rich than that. But it's possible that you could get even more rich structures by doing other things like having degree constraints, putting negative signs on some of the subgraph counts, or looking at other statistics that aren't subgraph counts. Okay, so this is maybe we have sort of we've fixed the model in sort of the simplest setting, but you might be able to get some richer structures by doing some other things. Okay, mathematically, I think the most interesting problem is to extend the results to have some of the parameters be negative. And then you need to analyze this optimization problem in the sort of lower tail for subgraph counts, which is pretty wide open at this point. Okay, and I'll stop there. So thanks for your attention.